Group 14, otherwise known as the carbon family or the crystallogens, is composed of the six elements carbon, silicon, germanium, tin, lead, and flerovium, with only the sixth being synthetic. In terms of periodic trends, the carbon family does conform well to general periodic trends, with atomic radii increasing down the group and ionization energies decreasing. The elements also get progressively more metallic, with carbon being a nonmetal, silicon and germanium being metalloids, and tin and lead being metals. These elements only have two electrons in their outermost p orbital, with them generally adopting oxidation states of +4, with the exception of the heavier elements, tin downwards, with Sn2 plus being unstable, but Pb2 plus otherwise. In terms of bonding, the element-element mean bond entropies decrease as you go down the group, and some elements in this group are capable of undergoing catenation, such as carbon and silicon. Carbon, element number 6 with an atomic mass of 12.01 AMU. It has a valence configuration of 2s2 2p2, normally taking on an oxidation state of +4. It is the only nonmetal in the group and has many allotropes with varying properties. Carbon is 19th in terms of abundance in the Earth's crust, but ranks second in terms of abundance in the human body, after oxygen. We shall take a look at three of carbon's major allotropes. Diamond is carbon in a cubic crystal system with a giant molecular structure, a density of 3.5 to 3.53 grams per cm cube, and a 10 on the Mohs scale. As its defining mineral, its melting point is pressure dependent. At 1 atm and 4700 degrees Celsius, it instead gets converted to graphite and subsequently sublimes to a vapor. Whereas at 99K atm and 5000 Kelvin, it would melt into liquid diamond. Graphite is carbon's most stable form at 1 atmospheric pressure, with a hexagonal crystal system and a density of 2.09 to 2.23 grams per cm cube. In contrast, it has a rating of 1 to 2 on the Mohs scale. Due to the nature of the bonding of carbon and graphite, for each hexagonal carbon layer, there will be a stray valence electron which is free to move through the structure, enabling electrical conductivity. As such, graphite sees usage as a relatively inert electrode. Other applications involve pencil lead and lubrication. Fullerenes are an interesting allotrope of carbon, with graphene and buckyballs falling under this category. They are technically considered a mix of single and double bonds, due to each carbon only having 3 and not 4 neighbors. Currently, most research is going towards the development of carbon nanotubes of high tensile strength and graphene derivatives for use in electrical components. Given the sheer number of reactions which carbon compounds are involved in, we shall instead look at processes relating to life. Carbon's electron configuration allows the formation of very stable bonds with oxygen and hydrogen, with these bonds storing great amounts of energy. Carbon fixation may occur in the form of photosynthesis, while carbon combustion may occur in the form of respiration. Silicon, element number 14 with an atomic mass of 28.09 AMU. It has a valence configuration of 3s3 3p2, normally taking on an oxidation state of +4, a melting point of 1414 degrees Celsius and a boiling point of 3265 degrees Celsius. Silicon is the first metalloid in this group. Metalloids look like metals but behave largely like nonmetals. They have intermediate to relatively good electrical conductivity and are semiconductors or have semiconducting forms. A semiconductor is a poor conductor in its natural state but can have its conductivity altered via doping, addition of certain impurities. Silicon is the second most abundant element in the Earth's crust by mass, right behind oxygen. It normally appears as silica or other silicates. Silicon has two common allotropes, amorphous and crystalline. Amorphous silicon is brown and powdery, flexible, but not especially strong. This is a result of dangling bonds, where silicon atoms would have too few neighbors to satisfy their valences. These silicon atoms are essentially immobilized free radicals, but elements like hydrogen and oxygen can replace these dangling bonds. Amorphous silicon is important in modern semiconductor device operation and is relatively useful in solar panels. On the other hand, crystalline silicon is metallic and gray, being used in solar panels and microchips. It comes in two forms, monocrystalline and polycrystalline. Monocrystalline silicon has a homogeneous crystal structure, while polycrystalline has many small silicon grains of varied crystallographic orientation. When silicon is doped with boron, aluminium, or gallium, it becomes a p-type semiconductor which creates holes in the silicon lattice that turns the material into a positive one, allowing for electron acceptance. On the other hand, the introduction of arsenic or phosphorus would lead to a free-moving displaced electron, which would allow for electric current to flow through, creating a negative type. The p-type and n-type silicon can be placed together to form a semiconductor junction or a one-way electric gate or a diode. If one were to connect the anode of the battery to the p side and the cathode to the n side, the depletion zone or neutral zone of the junction widens and it turns into an insulator. If one were to reverse the connection, you basically have an exchange of electrons internally, which allows for current to flow freely. Silicon also reacts vigorously with all halogens to form silicon tetrahalides. Silicon tetrachloride, for example, is an intermediate in the manufacturing of polysilicon, a hyper-pure form of silicon, which would later be used in the photovoltaic industry to make solar cells. Germanium, element number 32, with an atomic mass of 72.64 AMU. It has a valence configuration of 4s2 4p2, normally taking on an oxidation state of +4, a melting point of 939 degrees Celsius, and a boiling point of 2833 degrees Celsius. Germanium is the second metalloid in this group. Just like silicon, germanium is used as a semiconductor in transistors and other electronic devices. Germanium is often found as a brittle silvery white element, and this allotrope is dubbed alpha germanium with a metallic luster and a cubic crystal structure, just like diamond. Let's start looking at some reactions and compounds alpha germanium is involved in. As it's so similar to silicon, it can also be doped in a similar manner with the same compounds. When heated up, germanium can react with oxygen to produce germania, which has a high refractive index and low optical dispersion, making it useful in optics such as lenses. Germanium tetrachloride, on the other hand, can be generated by the dissolution of germania in concentrated hydrochloric acid. In the manufacture of optical fibers, silicon tetrachloride and germanium tetrachloride will be introduced with oxygen in order to slowly oxidize them into their respective oxides and form a glass mixture which makes up the inside of our optic cables. Tin, element 50, with an atomic mass of 118.71 AMU. It has a valence configuration of 5s2 5p2, normally taking on an oxidation state of +4, but being capable of going down to +2 where it becomes less stable. A melting point of 232 degrees Celsius and a boiling point of 2602 degrees Celsius, tin is the first metal in this group. Tin has 4 recognized allotropes, although only 2 are of much significance. Beta tin, like beta germanium, is silvery white and highly crystalline while being stable and ductile. However, unlike germanium, beta tin accounts for most tin you see around. Alpha tin is the most unstable form, being brittle, dull, and gray. It's created when very pure tin is cooled, and it's stable below 13.2 degrees Celsius, and has a cubic crystal structure. If this rings a bell, you'd find similarities once more between alpha tin and alpha germanium. Alpha tin is also semi-metallic, which means it has potential semiconductor applications. With that, let us consider some of the reactions and compounds which tin is involved in. When reacted with chlorine gas at 115 degrees, it forms tin 4-chloride, which is mainly used as a precursor to organotin compounds, which are used as catalysts and polymer stabilizers. These organic compounds are also used as industrial biocides. When reacted with steam, it produces hydrogen and tin dioxide, an amphoteric compound. Tin dioxide is often used as a catalyst for the oxidation of aromatic compounds in conjunction with vanadium oxide. It's often found in polishing powder and can be used as an opacifier and white colorant in ceramic glazes. With its low melting point, it's often paired with lead to form solder before being phased out due to lead's toxicity, but tin is still used in solder to this day. Lead, element 82, with an atomic mass of 207.2 AMU. It has a valence configuration of 6s2 6p2, normally taking on an oxidation state of +2. a melting point of 327 degrees Celsius, and a boiling point of 1749 degrees Celsius. Lead is the second metal in this group. Lead dioxide is a naturally occurring compound which aids in the production of matches, pyrotechnics, and dyes, also being used as an anode material in electrochemistry. Perhaps the most notable application would be its usage as a cathode in lead-acid batteries, being often used in cars. The heating of lead metal in air at approximately 600 degrees can produce another lead oxide, lead-2 oxide. It was primarily found in lead glass and was also used in cathode ray tube glass to block X-ray emission. Lead's high density, however, makes it useful as a form of radiation protection to shield against gamma rays and X-rays, being used in X-ray machines, nuclear power plants, hospitals, etc. A particularly notable lead compound would be tetraethyl lead, which used to be used as an anti-knocking agent in engines. That is, until it was discovered that lead toxicity levels were on the rise. Flerovium, element 114 with an atomic mass of 287 AMU. First discovered in 1999, it is an extremely radioactive synthetic element with unknown chemical properties, assumed to be a post-transition metal but possibly a metalloid. Following trends, it's been predicted to have an electron configuration of 7s2 7p2. The most stable known isotope of flerovium has a half-life of only 2.6 seconds, although nuclear isomers may have longer half-lives. Due to its high instability, we can only predict its properties. We predict it to have a common oxidation state of +2 and also being able to have an oxidation state of +4. It would likely be metallic, silvery white, or gray. Outside of basic science research, it sees no applications. Group 13 is the boron family, in which boron is the only metalloid while the remaining elements are metals. It includes boron, aluminium, gallium, indium, and thallium. Most melting points are lower than that of group 14, with the exception of boron, its only metalloid. In fact, gallium is in group 13, which is famous for having a melting point below human body temperature, so it can be melted in one's hand. In terms of rarity, group 13 elements are neither rare nor common, while group 14 elements are relatively abundant in nature, namely silicon and carbon, of course. Nitrogen family, in which arsenic and antimony are metalloids, while bismuth is the only metal. It includes nitrogen, phosphorus, arsenic, antimony, and bismuth. Phosphorus, similar to quite a number of elements in group 14, have several allotropes, namely white phosphorus, which has a cubic crystal structure like diamond, is waxy, pyrophoric, and highly toxic. Secondly, red phosphorus, which has an amorphous network and is used in matches. All melting points are lower than that of group 14. Abundance and rarity varies. Nitrogen is highly abundant, while antimony is somewhat rare.